All right, so let's take a look at this last section. So this is going to be a hypothetical, I fully admit, very hypothetical scenario about what would happen if we compounded more and more frequently. Sorry, I lost my Apple Pencil. That's why I was looking all over the place. What if the number of compounds were to increase from, annual to semi-annual to monthly to daily to every minute or even every second? We're going to look at what happens to that growth factor component of that formula from our previous page. So remember that since it's growth, that's why we have the 1 plus is there. And then those compounds are just going to be in the denominator getting divided, just like before, and also in the exponent position, just like before. The only difference here is, I admit, we are working under a hypothetical interest rate or percent rate of 100%. If the percent rate was 100%, then the R value would be 1. And that is what the very hypothetical thing is that we're looking at here. So other than that, I'm just going to plug in these values for N in both of these positions, and we're just going to record what we get. So if I go into Desmos, and on the first one, if I ask it for 1 plus 1 over, okay, the first one was annual, so that'd be 1 over 1, and then raised to the power of, again, annual is 1, so power of 1. So that first line in our chart, the answer is just 2. First answer is just 2. Okay. But then what if it's semi-annual? So if it's semi-annual, then the denominator is a 2, and so is the exponent. So now it's 2 and a quarter. Okay. So 2 and a quarter. Next up is monthly. So now the denominator is a 12, and the exponent is also a 12. In which case, the answer would be 2.613. 2.613. 2.613. Okay, next up is daily. So 365. So 365 on the bottom. Oops. 365 on the bottom. And also 365 on top. And we now have 2.7145. 7145. 7145. Okay, now the next one is every minute. So it's always funny. I know exactly how many minutes there are in a year because I like musicals. And from the musical Rent, there is a song that literally has 525,600 minutes. And that's how many minutes there are in a year. So I will forever know how many minutes there are in a year thanks to that song. 525,600 minutes. There we go. So exponent as well. 525,600 minutes. Okay. So now we have 7 or 2.7. Let's go. 18279. 718279. 718279. Now you might be wondering why I'm writing so many decimals, and it's because I want to make sure that I can tell the difference from one line to the next. Because watch what's about to happen on this last one. 31,536,000. Okay, I'm not going to have that one memorized. Let's see. So, what did I say? 31 million. I already forget. 31 million 536. 31,536,000. Up here as well, change that to 31,536,000. All right, so I'm going to write this down. I want to make sure I capture the decimals. So 2.7182818. So 7182818. 7182818. Oops. 7182818. Okay. So why was I paying so attention to those decimals? Okay, guys, take a look here. Even as the number of compounds got ridiculously huge every minute or every second, the actual growth factor for that didn't change very much. The difference between compounding every minute and compounding every second is almost not even discernible. They both just kind of look like 2.71828. Like they're almost identical, but you can tell the more and more decimals that you carry out, you can tell they're not quite identical. They are a little bit different, but barely. They're barely discernible. Now, I don't know about you, but this should come across as like unexpected. When I first looked at this, I was like, whoa, whoa, wait, this doesn't make sense. Because the more you compound, shouldn't it just be a bigger growth factor? Like the more compounds, the higher the number, right? I mean, I get why you'd think that because after all, that number is an exponent. And the larger the exponent, the larger the result. I mean, that's typically what we think, what we know. And that is true. I'm not here to claim that larger exponents don't typically yield larger results. But what you're missing here is that variable n, that really big number, is getting used in two ways. Yes, it's the exponent, but it's also getting divided. So that really big number of 31 million is getting divided and raised as an exponent. So let's think about what happens in the mathematics here. If you take 1 divided by a huge number, what are you going to get? What is one cookie shared with 30 million people? How much cookie does everyone get? Practically nothing, right? 1 divided by 31 million is so small, it's practically zero. Now, on the other hand, like we said earlier, what happens when you have an exponent of 31 million? Well, that typically gets huge. So the exponent component wants the number to get huge, but the division aspect of this problem wants the answer to get really, really, really small. So it's almost like it's this battle between this piece of the formula wanting to be almost nothing and then this piece of the formula that wants the answer to get huge. And the silliest but yet most easy way I can try to communicate it is it's almost as if that battle, it's like they shake hands and they're like, you know what? We're going to call it good. Let's stop arguing. You want to get really small. You want to get really big. You know what? It's pretty much a wash. Look at that. The number is hardly any different. There's almost no impact at all. Even though this number jumped as much as it did, it had almost no impact. And the reason is because you've got this battle. This element gets small, this element gets big. In the end, it hardly changes the answer at all. This levels out to just this roughly 2.71828. So that's the observation that we want to record here. So what do we notice is happening? Well, what we notice to be happening is that the growth factor, zoom in a bit. So the growth factor levels out even as the number of compounds is very large. The growth factor essentially levels out. Those are my approximation, equal to approximation. The growth factor is essentially 2.7. If I had to round it, I'd say 2.71828. Yep. All these numbers, they pretty much level out to 2.71828. Now, what does this mean? Well, what you're looking at is essentially you're imagining what if a situation could compound almost continuously. So we're compounding so frequently every minute, every second. Imagine if I were to be even more obnoxious and I did every millisecond, every nanosecond. I could get really obnoxious here. What we're trying to capture is just this idea of you're compounding so often that it's borderline continuously. I'm talking every moment of every day, continuously. If you have that situation, the formula takes on a new structure. And you're only going to use this version of the formula if it says continuous. So most of the elements are still the same. You still have the capital P, which is that principal or initial amount. So principal or initial. You still have your lowercase r, which is your percent rate in decimal form. Percent rate in decimal form. And then you still have lowercase t, which is your time in years. The newness of this formula is right here, this E. Okay, so that letter E, he's actually not a letter, he's a number, you'll see. But that little guy E, he is called the continuous compounding factor. So that is called the continuous compounding factor. And E is a number. So stay tuned, you'll see. E is a number. It's approximately 2.71828, just like we saw up there. That is what this was helping us to discover. When you have a continuously compounding situation, the growth factor is pretty much this, 2.71828. That is the growth factor. Now, because it's a value that's used and proven in mathematics, we call it the letter E. So you know how at some point in your mathematical career you learned that pi was a number? You just kind of had to accept it. It may have felt weird at first, but eventually you're like, yeah, pi is a number, 3.14. Well, same thing. You're officially at the time in your math career where you now know E is a number. If you go to Desmos and just go to your regular keyboard and type E, yep, there you go. 2.71828. It goes on forever, just like pi does. It's called an irrational number. E goes on forever, but it's a number. Every time you type E in any calculator, it knows you're talking about a number. So that is what this formula has, is that continuously compounding value of E. Now, again, I can't stress this enough. You're only going to use this version of the formula if it says continuous. If the problem does not say continuous, for the love of Pete, don't use this formula. You only use this formula for continuous. So for instance, look at number 4. It says, how much money would we have with an initial deposit of $5,000 and it was compounded continuously? Ding, ding, ding. See that phrase? That's what tells me I'm using the formula with E. Any other problem that said quarterly, daily, monthly, right? Then you're just going to use the typical compounding interest. It's only ones that say the word continuous that you're going to use this version. But this one does say continuous, so I know that it's going to be safe. So what do we have? The initial investment is $5,000. It is continuous, so I know my growth factor is E. The interest rate is 0.038. They're 3.8% in decimal form is 0.038. And I'm going to leave my money in there for 7 years. So if I just type all this in Desmos, 5,000, I'm going to zoom out. There we go. So 5,000 E and then to the 0.038 times 7. There we go. 65, 23, 67. 65, 23, 67. 65, 23, 67. That is how much money would be in that account if it was compounded continuously for 7 years. Okay, last but not least, question 5. How long would it take us to double our money in this very same account? Okay, so I'm still going to invest $5,000. It's still growing continuously at a rate of 3.8%, except this time, how long does it take? I don't know how long it takes. It's not going to be 7 years. In fact, I already know it's going to take longer than that. I'm not going to double my money in 7 years. Nope, it takes longer. How much longer? I don't know. So, this is where you just have to admit to yourself that you don't know how long it takes. Use a variable. But you do know that your financial goal is to double your money. So, $10,000, that's your desired final amount. So this is the setup. Now, how we solve this is going to be the same as everything else in this chapter. We're not doing it algebraically, so we do need to rely on Desmos. I'm going to put all of this into line 1 of Desmos, and then in line 2, I'm going to tell Desmos that I want an output value of 10,000. So let's put this in Desmos and see what we get. Close all that out. So 5,000 e to the 0.038 and then times x. So just admit that you don't know what it is. And then in line 2, we have a desired output value of doubling my money. So 5,000 times 2 is 10,000. And that right there is going to be our answer. So 18.24 looks like 18.24 years. So back here, I get my answer as 18.24 years. That is how long it takes to double our money. Put this in Desmos, and then we touch the intersect. Oh, you know what I didn't mention really quick? Sorry. The window on this, just in case you were on a home screen and you're like, where's my graph? And then you're lost in window hell, right? Don't get lost in window hell. Same thing as before. Let's go to the wrench. The x-axis represents time, 0 time, all the way up to, well, let's hope we reach our financial goals within our lifetime again. So maybe like 50 years would be plenty of x value. And then the y-axis represents the money. Remember, you put in 5,000 and you're hoping to get 10,000. So 5 to 10 would be an appropriate range. I'm going to give myself a little bit of wiggle room. I'm going to say 4,000 on the low end and maybe 11,000 on the high end. Just something that covers the 5 to 10,000 range. And that is how you'll get a pretty good window of this. Notice I'm still kind of pinching and zooming a little bit, but as long as you can see that increasing red curve and then that straight across horizontal line at 10,000, that's what you want to see on these. And once again, we get the 18.24 years. Okay. So there we go. That is a wrap on those topics. And now you guys have some homework type tasks to hopefully practice these. And yeah, if you have any questions, of course, just ask. Thank you.